Master node component scheduler. The role of Kubernetes scheduler is to assign new workload objects, such as pods, to nodes. During the scheduling process, decisions are made based on current Kubernetes cluster state and new object requirements. The scheduler obtains from the etcd data store via the API server resource usage data for each worker node in the cluster. The scheduler also receives from the API server the new objects requirements which are part of its configuration data. Requirements may include constraints that the user and operator set, such as scheduling work on a node labeled with disk equal to SSD key value pair. The scheduler also takes into account quality of service (QoS) requirements, data locality, affinity, and anti-affinity, tent, toleration, cluster topology, etc. Once all the cluster data is available, the scheduling algorithm filters the nodes with predicate to isolate the possible node candidates, which then are scored with priority, in order to select the one node that satisfies all the requirements for hosting the new workload. The outcomes of the decision process is communicated back to the API server, which then delegates the workload deployment with other control plane agents. The scheduler is highly configurable and customizable through scheduling policy, plugin, and profiles. Additional custom schedulers are also supported. Then, the object's configuration data should include the name of the custom scheduler expected to make the scheduling decision for that particular object. If no such data is included, the default scheduler is selected instead. A scheduler is extremely important and complex in a multi-node Kubernetes cluster. In a single-node Kubernetes cluster such as the one explored later in this course, the scheduler's job is quite simple. Master node components, controller managers. The controller manager are control plane components on the master node running controllers to regulate the state of the Kubernetes cluster. Controllers are watch loops continuously running and comparing the cluster's desired state, provided by object configuration data, with its current state, obtained from etcd data store via the API server. In the case of a mismatch, corrective action is taken in the cluster until its current state matches the desired state. The kube controller manager runs controllers responsible to act when nodes become unavailable, to ensure path counts are as expected, to create endpoints, service accounts, and API access tokens. The cloud controller manager runs controllers responsible to interact with the underlying infrastructure of a cloud provider when nodes become unavailable, to manage storage volumes when provided by a cloud service, and to manage load balancing and routing. Master node components. Data store. etcd is a strongly consistent, distributed, key-value data store used to persist a Kubernetes cluster state. New data is written to the data store only by appending to it. Data is never replaced in the data store. Obsolete data is compacted periodically to minimize the size of the data store. Out of all the control plane components, only the API server is able to communicate with the etcd data store. etcd CLI management tool, etcd CTL, provides backup, snapshot, and restore abilities, which come in handy, especially for a single etcd instant Kubernetes cluster, common in development and learning environments. However, in stage and production environments, it is extremely important to replicate the data stores in HA mode for cluster configuration data resiliency. Some Kubernetes cluster bootstrapping tools, such as kubeadm, by default provides stock etcd master nodes, where the data store runs alongside and shares resources with the other control plane components on the same master node. etcd scheduler, control manager, API server, worker nodes points to load balancer. Stack etcd topology. For data store isolation from the control plane component, the bootstrapping process can be configured for the external etcd topology, where the data store is provisioned on a dedicated, separate host, thus reducing the chances of an etcd failure. External etcd topology. Both stack and external etcd configuration supports HA configurations. etcd is based on the wrapped consensus algorithm, which allows the collection of matches to work as coherent group that can survive the failure of some of its members. At any given time, one of the nodes in the group will be the master, and the rest of them will be the follower. etcd gracefully handles master election and can tolerate node failure, including master node failure. Any node can be treated as a master. etcd is written in Go programming language. In Kubernetes, besides storing the cluster state, etcd is also used to store configuration details such as subnet, config maps, secret, etc. Master node components, API server. All the administrative tasks are coordinated by the Kubernetes API server, a central control plane component running on the master node. The API server intercepts RESTful call from the user, operator, and external agents, then validates and processes them. During processing, the API server reads the Kubernetes cluster's current state from the etcd data store, and after a call execution, the resting state of the Kubernetes cluster is saved in the distributed key-value data store for persistence. The API server is the only master plane component to talk to the etcd data store, both to read from and to save Kubernetes cluster state information, acting as a middle interface for any other control plane agent inquiry about the cluster state. The API server is highly configurable and customizable. It can scale horizontally, but it also supports the addition of custom secondary API servers, a configuration that transforms the primary API server into a proxy to all secondary custom API servers and routes all incoming RESTful code to them based on custom Define rules.